Hello together and welcome to the video presentation of my paper Reconstructing Facial Expressions of HMD Users for Avatars in Virtual Reality. To put this rather technical appearance title into context, we first need to talk about the subject of computer-mediated communication. Now, computer-mediated communication is ubiquitous and we use it every day when taking our smartphones out of our pockets to call someone or to just write a text message. However, for probably many of you, pictures like this might come into your mind. Classical remote conferencing tools such as Zoom or Teams. Few of you might think about this, avatar-mediated communication, or especially avatar-mediated communication in virtual reality. If you believe Facebook or Meta, this is the future way to communicate. So, while for some of you this might be a dystopic thought, this nowadays niche of computer-mediated communication has definitely some advantages compared with video conferencing. Everyone knows the partial awkwardness of using video conferencing software. We experience annoying technical issues such as interrupts, low bandwidth, and this resulting bad audio or video quality. But we also, and this is maybe the even bigger problem here, experience constraints in nonverbal communication and the way social signals are conveyed. We all know the disturbance of missing eye contact, for example, but also factors like nonverbal synchrony or spatial behaviors are some pain points. And communication mediated by avatars in virtual reality can help here. However, this requires technologies to sense a participant's social cues and an authentic three-dimensional representation of the participant that can also convey these sensed social signals in a shared virtual environment. Now what you see here is a shot from a social virtual reality project at our university. However, in many current commercial applications, such as social VR platforms, this goal is tried to be achieved but far away from being perfect. Well, at this point, I can refer back to the title of the paper, Reconstructing Facial Expressions of Head-Mounted Display Users for Avatars in Virtual Reality, since facial expressions are crucial social cues that emit essential information about emotions and relation and to build rapport. They are the most fundamental basis for credible avatar-mediated communication in virtual reality. Thus, we want to present our approach, which covers a holistic system that controls the aspects of the processing pipeline from the real-time image-based tracking of facial features to the creation and animation of a realistic 3D face model of an avatar. But let me now show you our approach to the problem. Here we see to the left our facial expression tracking component, which is able to communicate with our avatar that is rendered and controlled via the Unreal Engine via an interface which is closely adapted from the facial action coding system, or short FACS. I know this picture is quite small here in the figure, however this is essential. FACS is basically a system to taxonomize human facial movements by their appearance on the face. Small excursion, in this table we see the main FACS code sorted by action units. The action units are the fundamental actions of individual muscles or muscle groups. And using FACS, nearly any anatomically possible facial expression can be coded and be deconstructed into the specific action units and their temporal segments that produce this expression. Now, using this system turned also out to be a useful standard for face tracking and blend shape based avatar modeling. For example, the Y Facial Tracker or the Apple AR Kit adapt and augment the FACS system. So that's what we did too. We built a system to detect action unit activation and modeled an avatar's face based on the FACS, on the anatomy described. To do so, we went with a machine learning based approach in which we connect several artificial neural networks in series. In contrast to other approaches, we went with an approach using just an RGB camera, RGB data, and no depth channel like many others. And as we see in the figure, our first step is the detection of our region of interest in a raw RGB picture. In this case, this is the lower face, respectively the mouse area within. Then, within this mouse region, we search for anthropological landmarks, face landmarks, and based on these, calculate an active appearance model. After that, based on the temporal active appearance, we compute the level of action unit activation of the relevant muscle groups following the FACT standard. This is basically a value between 0 and 1 for every included muscle group. I will come to that later. These values have now to be processed by the avatar face model to activate its blend shapes, and I will come to that later too. So our first component is for the sensing of the lower facial expressions. As I mentioned before, we use a machine learning based approach, in our case supervised learning methods, and now these require a large amount of labeled data, whereas the required annotations in the dataset vary for the multiple steps in our detection pipeline. Basically, we found two kinds of datasets useful. First, datasets of RGB pictures of faces labeled with anthropological facial landmarks, and second, datasets of RGB pictures labeled with facial action unit activation. For the anthropologic face landmarks, we found matching datasets in the iBug V300 as well as a dataset from Kaggle for facial key points. Both datasets provide pictures of faces annotated in the 68 facial landmark notation, which gives us information about where in the RGB picture certain facial features are located. For the facial action unit activation, we found a dataset recorded and labeled in China very useful, and that's the favorite dataset that also includes RGB pictures of faces annotated with a continuous action unit activation, also close to facts. The continuous annotation with the floating values here in this dataset between 0 and 1 made us prioritizing this dataset before, for example, the FERA dataset or the DISPA dataset, where these action units are annotated only categorically. So let's come to augmentation of the training data. So we got datasets with pictures of faces of people, okay? Now, for the purpose to detect the mouth in a face that is partially occluded with an HMD, these pictures contain incorrect information as the people on these pictures are not wearing HMDs. So here we went with an approach you might have seen in another context using COVID mask detection. So just instead of augmenting COVID face masks to the pictures, we augmented HMDs to the V300 and the Kaggle dataset. And in our case, we used Vive HMDs, which we used for development. We did this just using the information about eye and nose position coming from the 68 landmark annotations, and then we placed, scaled and rotated the HMD overlay picture accordingly. So resulting, we have a dataset of combined 10,300 people wearing HMDs. For the favorite dataset, that includes 99,300 pictures, we excluded annotated action units concerning the upper face, as they are obviously irrelevant for our purpose. Then we redefined the assignment of the remaining, as you can see in this table. So, as our training set now contains the right information, it is possible to train our first artificial neural networks to detect the mouth area of a face occluded by an HMD. For this purpose, we chose a common approach using convolutional neural networks. In this context, we found the VGG16 network useful, as it has been proven successful in tasks for large-scale image and video recognition and also region estimation. What we did then is to take the flattened output layer of the VGG16 and added 3 dense layers, and then created a 4-unit output layer describing the normalized coordinates of the bounding box around the bottom of the face or the mouse, respectively. In the next step, we need to find the required anthropological facial landmarks within our predicted lower face area. Here we reduced the 68 AFLs from the training set to only 37 relevant ones for description of the lower face. For landmark recognition, we found the D-lib shape predictor as an adequate tool. The D-lib shape predictor uses a histogram of gradients and an ensemble of regression trees algorithm, which is showing for this application higher accuracy and a better real-time performance than, for example, CNNs that could definitely also solve the problem here. The output of this step is the detection of 37 facial features in XY coordinates that describe the shape of the jaw, the nose, and the mouth. In the last step in our process, we have the prediction of the face muscle activation in adaptation to the FACS system, based on the facial features we recognized in the previous step. Now, there are again several methods to approach this issue. You can go with a CNN, for example, but we found it useful to go with an active appearance model. The active appearance model we created is consisting of 8 polygons based on our predicted 37 anthropological facial landmarks, while here we excluded some that we thought were unnecessary, as you can see in the figure. Anyways, our 8 polygons consist of 43 two-dimensional vectors, which we used as input vector for our neural network. We used a simple 3-dense fully connected neural network to predict the activation of the remaining 14 action units on our output layer. And those are eventually describing the level of muscle activation of the lower face. Okay, now let's have a quick look on the results. Here we see the different stages for the face muscle activation prediction, the data sets and algorithms used, input and output of the networks, and the prediction accuracy and the relevant metrics. We see in stage 1 we got an intersection over union of 0.91 for predicting the mouth area. For AFL prediction in stage 2 using D-lib we got a mean average error of 0.52. And for the prediction of the facial action units using our AMM, we scored a mean squared error of 0.015. These are all pretty decent results. However, these results are to be taken with a pinch of salt. I will come to that later. Here I have a small or a brief excerpt of the recognition in real time. Okay, so now let's quickly talk about our second component, the avatar, or the rigging animation basics of the avatar's face. As stated in the beginning, there is still a lack of realistic rigged avatars for avatar-mediated communication. So thus, we created a new avatar from scratch, and for that purpose we found usage of 3D scanning methods crucial to achieve the best results for self-representation. For our face scan, we used the reality capture to quickly and easily create a 3D model and export textures and polypaint. We then created a character base match, unwrapped the character model, and created UV maps. To match the base mesh with the created scan model, we projected the character's base mesh onto the scan, and then we adjusted the base mesh, subdivided it, projected it again until we had all details transferred. And this is how the results look like. The character base mesh finally consists of 32K vertices, of which almost 12K are just for the head area. This is in line with nowadays general game engine recommendation. A few words considering the character's face rigging. We started with facet blend shapes as the basis. However, we only used few of them, of the base model blend shapes, for further development. We had actually to create the majority of the blend shapes completely from scratch by hand for achieving the best results. So here we see excerpts of the components interplay. For each of the 4 divisions, we show left the computed AU activation as a result of our machine learning pipeline. In the middle, the real-time facial scan displaying the mouse and the LFL detection, as well as the AMM, and through the right, the resulting animated avatar facial expression. Considering the AU activation numbers, it is visible, I mean this is quite small but we can probably see it, that the neutral facial expression in the top left shows almost no activation, all values are close to 0. In the top right picture we see, for example, the jaw drop, the upper lip raise and lower lip raise AUs are activated, while in the angry face in the bottom left we see only the upper lip raise and the lower lip depress AUs to be activated. And in the bottom right picture we see slight activation of the interacting action units, lip corner, pull stretch, upper lip raise and lower lip depress. Yeah. You might notice that there are also small activations of action units that are not involved in rendering the facial expressions. This was accepted to a certain degree, but it's also, of course, minor error in recognition. Okay, so we see that the concept works in its entirety. We can track the lower facial expressions of an HMD user and transfer it to the face of an avatar. There are some limitations though. First thing to mention is the jitter effect, as you probably have seen before in the short video. This is because the prediction errors accumulate over the 3 stages. So if the mouse region prediction is not accurate, AFL detection will be even less accurate, and thus also prediction of the AU values will be even less accurate. Our MM was created based on trials and simple approximation of the facial muscles to our best knowledge and not really research based, so that is also a quite bad limitation we have to focus in the future. Additionally, the FAFRA dataset only contains faces of Asian ethnicity, so although we have an AFL based abstract representation of those, this still might cause a bias. One more major point to mention is missing hyperparameter optimization. If we would optimize hyperparameters, this offers chances for huge accuracy improvement for all 3 recognition steps. So a quick look onto our plans for the future. Of course, we want to deal with the limitations stated before, especially hyperparameter optimization and AMM optimization. And furthermore, we also want to take animation for the upper facial expressions into account, which are covered here. And we want to add a 4th step in our recognition pipeline to achieve a classification of emotion based on the facial expressions. Okay, thank you for listening. That was it from my side. And I think we are ready for some questions now.